Well, good morning, everyone. Good morning, good afternoon, and even good evening for those of you across the ocean, especially our guests today. Welcome to today. I think it's our 11th Moberg Analytics case studies in Neurocritical Care AI web series. Thank you all for joining live or catching us on the replay. Um, just to do a little bit of a recap, the reason we're doing this is we understand that, treating and understanding brain injury is a gigantic mission that you all are embarked upon. And our goal as a company is to help in that mission in however we can. And these webinars are an extension of that goal. So we do things like bring amazing guest speakers on to talk about how they've attacked problems in neurocritical care using AI and machine learning and that kind of thing. To serve as kind of a tutorial, so you can maybe apply some of these techniques to your own problems and your own data. We like to provide case studies and examples. In some cases, we're able to provide data that you can use and sample notebooks. And also we're accepting applications for kind of in-kind starter grants. So if you need a place to work on some data and some tools and some consulting to get a project, to get a research question off the ground, we're here to help. So that's all part of our goal as a company, is to do that kind of thing. If you have any feedback at all about the webinars, please use the QR code or the links or the email listed on the screen right now. Also, the smart people are in the audience. We are not the ones who understand this and know this. So if you would like to volunteer to speak and share some of the techniques you've used, or the problems you've attacked, or that kind of thing, please reach out to us. We would love to have you help us advance this field as much as we can. We've got quite a little library of replays that we're building up now. So these are available via the link off of our website. Also, we've got some of the, if you should have received an email if you're on if you're on this list, if you're on this call, with instructions on how to sign into our portal and gain access to some of the sample notebooks, sample data, and things like that. So if you haven't received that, please reach out to me, Craig, and we'll get you set up. If you have any questions today, please use the Q&A feature on the Zoom menu that we all are very familiar with. And so without further ado, we are really excited today to have our guest, Dr. Jeanette Tas, as today's speaker. She is a technical physician and a postdoc researcher at Kepler University Hospital and Kepler University in Linz, Austria, under Raimund Hellbach. Her clinical and research focuses are the implementation of multimodal neuromonitoring and data analysis in neurology and neurocritical care. And we met, I know the first time I met Jeanette was last year at the ICST, the Spreading Depolarization Conference in Hungary. I'm not sure if Dick and Ethan, who that was their first time meeting her, but it was mine. And we soon found out that she is very passionate and very energetic about multimodal monitoring and data analytics, which meant she was kind of just our kind of person. We worked with her in developing some of the dashboards that you might see in our clinical platform. She was very enthusiastic and gave us amazing feedback on developing what those dashboards look like and how they can be useful at a clinical level. And now we're working with her at Linz as part of the multimodal monitoring program that she's establishing. So anyway, she's great fun, and she's been a great friend to the company, and we were lucky enough to see her just a couple of weeks ago in Cambridge. Today, she's going to talk about unsupervised clustering and how it can be applied to neurocritical care. Two notes. The work that she's going to present has been submitted for publication, but it's still in review. So we won't be posting the replay immediately upon the session, but we will wait until it's been published finally and we get the word from Jeanette. And also apologies from Dick and Ethan, who very much wanted to be on today's call, but they are attending a conference in Chicago and are unable to make it. So anyway, with that, welcome and thank you very much, Jeanette. I will stop blathering on and turn the floor over to you.
Hello?
Yeah,
I think
we
it's
can hear you.
working, right?
Yeah,
Many
we can hear
thanks,
you.
Greg, for this introduction. I will share my screen. Let's see something. Okay. Seems that I can't share my screen.
Uh,
Maybe I should.
Oh, host and panelist. Okay.
Yes.
Try
Now
now?
I
Okay,
can.
sorry.
Yes. No, it's okay. Let's see. So you can see my screen, right? My full
Yep,
screen.
perfect.
Perfect. Okay. Shall I turn on my camera? Maybe. Oh, that's not possible. Okay. Okay, I can't turn on my camera because there's something with the host. But then we don't do it without camera, I think. Usually it's possible, right? Okay, no. So sorry for this. But yeah, so thank you, Craig, for this introduction and also for the invitation of this to give a talk. As already mentioned, I'm a technical physician, so not a dedicated data scientist, as said, but I think this aligns well with the focus of my talk today. And unsupervised clustering, yeah, so this started actually when I started working in Linz over a year ago together with Professor Raymond Helbok. And I read at that time a study from Akkerlund et al. In which he applied unsupervised clustering, which he applied with a center TBI data set. And I got interested in this method as I thought it may be a very promising method to apply for multimodal neuromonitoring data. So today I hope that I can answer this question slightly. If unsupervised clustering is a promising method for neurocritical care data and in particular multimodal. So, but first to put this big data into context, Morris et al. He counted the number of variables that is available for one patient admitted to the ICU. And he counted for one patient 236 variables, which is available to make decisions on. But of course, our working memory is limited to just a few variables and well about 3 variables to make clinical decisions on. So what can we do with the rest of these data? Of course, we can use it to use it for research purposes. And to process all these big data, various machine learning techniques exist, and 2 of them are supervised learning and unsupervised learning. Also, semi-supervised learning exists, but just to keep it clear for everybody. So for supervised learning, it requires predefined labels, which is, for example, in regression analysis, that you have like the input variables, the independent variables, and the outcome variables. Both are known, for example, functional outcome. But in contrast to that, when you look at unsupervised clustering, the input features, they are known, and you put them in your analysis, but the output or the labels are unknown, so not predefined. And this allows us to discover new phenotypes as it groups data from patients with similar characteristics into clusters. my talk today will be divided in two parts. So first, basic background about unsupervised clustering, and this will then set the stage for my second part, the systematic review that we performed. So, well, if you are really familiar with unsupervised clustering, then you can maybe check your emails now or whatever. But otherwise, I will start with an example. So there are various patients admitted to an ICU. They have, for example, intracranial pressure monitoring and blood pressure monitoring. And the question can be, are there groups of patients with similar monitoring characteristics that may benefit from a certain therapy? So then, to answer this question, you can apply unsupervised clustering and find, for example, two, or you can obtain two groups, like patients with slightly higher ICP and a group of patients with slightly lower ICP. So what does this tell us? Well, it tells us at least that patients in cluster 1 are more similar to each other than compared to the patients in cluster 2, which is, of course, of interest, for example, when you think about individualizing therapies, as some therapies might work for some groups of patients compared to the whole group. But how do you come to this result? So now I will explain for that one method in detail, not that you need to replicate it as that, but just to get an idea also about the decisions that you have to make when you apply clustering. So the simplest example to understand is with k-means, which is a traditional unsupervised clustering method like hierarchical clustering. And this method works as follows. So let's say you start with this data set in this two-dimensional space. And in the first step, you initialize your clustering, which means you decide which, how many clusters you would like to have. And this is shown in here. So you start with two clusters, which are called the centroids. So you project these centroids randomly to your data set. And then you have to decide, okay, which data points are fall in the red cluster and which one in the yellow. So you can decide that by yourself, of course, but this is not really reliable. So in the second step, you compute the distance from each data point toward both centroids, and the closest distance to one of those centroids is the cluster where it allocates to. So in this case, you have this red cluster and this yellow cluster. But in step 3, there happens something with the centroids. As the centroids, they move towards the middle of the cluster. So you compute the middle, the average value within either the red or the yellow cluster. And this is the location of the new centroid. And then you have a situation like this in step 4. But in step 5, you again compute the shortest distance of each data point toward a centroid. And what you can see is that 2 data points moved from the yellow cluster towards the red cluster, as now the distance towards this red centroid is the closest. And then again, you compute the average value of the centroid, because this is now a different value since these data points move cluster. And this is repeated for x times until you get a situation that the centroids are the middle of the cluster and the data points are the shortest distance towards this centroid. So this is then your final result with 2 clear clusters. And as I mentioned, I wanted to show that the result depends on various choices or assumptions of the configurations. And so I started with explaining this method that you have to preset the number of clusters. As I said, we choose 2 clusters, but we also could have chosen for 3 or 4. And you have also the calculation method of the centroids. So we use k-means, but you also have like k-median that you compute not the average value within the cluster, but the median value. And then you have that k-means is only applicable for numerical values. And you also have the limitation that for k-means in particular, you have always spherical and equal variance clusters since you compute this distance. And finally, you have different distance matrices. So most studies use the Euclidean distance to compute the data point towards the centroid, but you can also use like cosine distance, dot product, and so on. So these are all where you have to think about before you start with k-means. But besides the variations in the configurations, there are also various methods for unsupervised clustering, of course. And this is, now I want to show you 4 main methods of that. And this partitioning clustering is the clustering what I already explained. So it includes the k-means. With this, it has its advantages and restrictions. But you have also like this hierarchical clustering, and instead of predefining the number of clusters, you choose or you select the number of clusters based on the result in the dendrogram. So you look at this dendrogram and you can decide, okay, this branch is clinically relevant to interpret my data, which has a restriction when your data is really complex or a large data set that you can hardly visualize it. Then you have this density-based clustering. So this has overcome some limitations of the k-means, so it's not restricted to these equal variance and spherical clusters, but you can have different shapes of clusters, what has, of course, advantages when your data has no equal density. And the most complex method, I would say, is the model-based clustering. And this is a more novel method. So instead of computing the distance, like with k-means, but also hierarchical clustering, it estimates the likelihood that a data point belongs to a certain cluster. And this has the restriction, as I mentioned, it can be challenging to interpret these results. So to summarize this first part, unsupervised clustering, it allocates data points to groups based on similar characteristics. You have various methods, various configurations, and the method selection depends roughly on the research question and the data characteristics. So now move on to the second part, and that is our unsupervised clustering systematic review that I performed together with Verena Ras and among others also Professor Helbok. And Verena Ras is also joining us, as she said to me. So our primary objective of our review was to provide an overview of unsupervised clustering applications. So we wanted to know, okay, what has already been done in the literature? And this secondary objective was that we wanted to discuss considerations for future studies. We included patients that were admitted to the ICU, like across all ages. They had an acute brain neurological disease. The study aim and objective was related to a clustering method, which also means that we only included studies that used intensive care unit data, and we excluded studies including patients with a secondary diagnosis of brain injury, for example, COVID patients where they were interested in the neurological symptoms, and we excluded reviews and meta-analysis and study protocols. So our study was pre-registered and we searched for 3 platforms. We used the following search terms, and Verena and I, we both screened the studies, and one reviewer extracted the study results. So this is our study selection flowchart. We screened over 1,000 abstracts. We end up with 18 studies, of which 3 studies were found by screening the references and the citations. And I would like to mention that we excluded 8 studies, which were ICU patients, but they did not include ICU data, so we excluded them. And this figure on the left shows the various included diagnoses. So to clarify this, on the y-axis are the number of pathologies. That means that 12 studies included TBI as a single disease, but there were also quite a lot of studies that used a mixture of diagnoses. So 5 studies in this case were subarachnoid hemorrhage patients, but they also included like either TBI, ICH, etc. On average, the studies included 42 patients with an interquartile range of 23 to 313. And on the right side, you can see in which year the publications, which year the studies were performed. So in the last years, most publications were performed, which is as expected. Identified 4 groups, but a single study could belong to multiple groups in this case. So first, the various studies assessed the feasibility of identifying differentiating patterns. Like for neuromonitoring data, they looked at intracranial pressure data over time, for example. But there were also studies primarily interested in biomarkers, so whether intracranial pressure morphology can be a biomarker for ventriculitis. Studies that developed as standalone algorithm, so as we defined it. And there was one study that tried an unsupervised clustering in combination with various processing steps to detect burst and suppressions in individual patients in order to quantify the sedation depth. But most studies, 12 in total, they focused on prognostic markers of specific phenotypes, such as aiming to enhance an existing outcome predictor. So now you have seen some examples what has been studied, and we were interested also to summarize all these results in one figure. And this is what we did in this alluvial plot. So 18 studies in the first column, you can see they are alphabetically listed. And in the second column, you can see the various methods. So from the traditional methods like k-means, hierarchical clustering, towards these novel methods, which includes then, for example, this Bayesian approach. And in the third column, you can see the various data sources that they used. And you can see that not only monitoring data was used, but also, which is as expected as you include only ICU studies, but they also combined it with imaging, demographics, etc. So they either use a single data source like only EEG data to cluster, but also combinations. And in the final column, you can see the functional outcome. So we were interested how many studies find significant differences in functional outcome comparing the clusters. So just to go back to my initial example, if you have 2 clusters, you can look, you cluster monitoring data, for example, you look what are the characteristics of these data, these clusters, and you look, are the clusters significant, different, yes or no? And so most studies, 9 in total, found a significant difference between the clusters. And then the last part of our review is we looked at the considerations for neurocritical care studies. So I started my talk by mentioning, well, my interest in multimodal neuromonitoring and unsupervised clustering, but we found only 3 studies that include 2 or more neuromonitoring modalities. This may be due to the need for a substantial number of patients, of course. So this might be improved for future studies. Second is the evaluation. So we also try to assess the quality of the studies, but due to the heterogeneity in reporting the methods, this was really challenging. So Kambert et al., he explained how you should or how you could assess clustering results. And he described 3 categories of assessment, like the tendency, the quality, and the stability. So just briefly, the tendency is you need a certain trend in your data. So like when you have random data or a lot of noise in your data, this makes it complex to cluster. The quality of the data is so you compare, for example, your results with a ground truth, which can also be challenging if you you apply unsupervised clustering, but sometimes this is possible as well. Internal validation is also like the assessment of the compactness of the clusters. This is also part of the quality, and then the stability is the assessment of the clustering result to various parameter configurations. So like the optimal number of clustering, I mentioned before that you select 2 clusters, but there are also methods to which makes it more objective to decide what is the optimal number of clusters. And then validation studies. So what is really important is that you validate your results with, for example, a different cohort because of the decisions that you have to make when you apply unsupervised clustering. And in the current studies, these external validations with different cohorts were only done in 1 study. So the take-home message then, is clustering a solution for neurocritical care big data? Yes, well, unsupervised clustering, it is possible to identify these phenotypes and endotypes also in neurocritical care, and especially in these TBI patients. They have various data streams were used for it, so this seems also very positive. It's also promising in understanding pathophysiology and prognostics, but you need these validation studies as unsupervised clustering results are dependent on the author's choices, which I hopefully have clarified. So that's it. Thank you.
Awesome. Thank you so much, Jeanette. Excuse me. We can open it up for questions now. If anybody has any, they can post them in the Q&A, or we can raise your hand and we can take you off mute if you want to speak out. I was curious. What was your goal in embarking on this? Are you trying to determine if this is the right approach for your own research, or where is this going with you at Linz?
Yeah. So actually, this was this is a funny question, because actually I wanted to apply unsupervised clustering, and then I realized, okay, but I don't know how to do it, and then came the question, what is already been done? And then we start, reading, and so now it's like a systematic review. So we initially wanted to apply clustering, and I still will do this, but now I know a bit more about it, and also about the limitation in particular. But still, I believe that this is a relevant method to have new hypotheses, and that you think that you can build on. So.
Cool. I was talking with Ethan and Dick last week, and I was just amazed that the people who have to the level of study that it takes in this alternate field to you're already studying probably the hardest field on the planet, right? Neurocritical care. And then to have to study, machine learning and AI and all this stuff too, just to do your field. I don't know if I would do as well in my field if I have to learn how to do neurocritical care just to do my field. A question from the chat: what sort of features turned out to determine clusters in your review?
Sorry, the last part.
What sort of features turned out to determine the clusters
So you mean turned out to determine clusters in your review, like the input features, or?
The question just says what sort of features. So I assume
like if we talk about the or what shows to be relevant, or but because the input features were like mostly included were like intracranial pressure monitoring, and then all sort of like waveform data, average values, but also PRX was included, etc. Is this answering the question?
I'm not sure. The questioner will have to let us know if we're answering the question or not.
Not so.
Yeah. Cool. So if anybody else has any more questions, please raise your hand or post in the QA. So I guess would one possible goal of this then be to look at clustering of disease and then looking at treatments and trying to start to differentiate treatments based on the clustering? Is that a possible, like when you look at, far down the road, if we, with more research, is that something that we would use clustering to help look at? Have I lost you? Uh-oh. Uh-oh, we lost Jeanette. Hopefully she'll dial back in and we'll follow up. I see the follow-up questions in the chat. Hopefully we'll get her back in here. There she is. Are you back?
Yes, sorry. I
No
don't
problem.
know. I've never had this. Okay.
So we had some follow-up on the question about features. To follow up, many clustering methods determine which input variables or combinations of input variables are most important to determine a cluster. For example, you could see that poor outcomes had been in a combination of patients with high ICP and low MAP.
Yeah. So in this case, you mean? Like, so they were like various. So for example, there was one study, and this was I found a very interesting study. They looked at intracranial pressure over time. And so this is not really a combination, but they found that so both high ICP trajectories and both low ICP trajectories were related to a poor outcome. So this is, for example, one example of this. And there was also one study that looked at microdialysis, and they clustered the microdialysis data, and they looked also at the comparison with cerebral perfusion pressure and intracranial pressure, and they did not find any significant difference between the clusters and these microdialysis data, but they only included 26 patients. So, well, yeah, there were some studies that included quite a number of patients, like the study from Akkerlund, 2 studies, but quite a number also included limited number of patients, which is also, for some studies a limitation.
Thank you. Cool. Well, thanks for the comments. If they're just going to wait for us another minute and see if we get any more questions. Okay. Well, Jeanette, thank you so much for coming on and explaining this to us. You always learn something new. This is fantastic work. And we look forward to seeing the results published. And we look forward to seeing you again soon, hopefully.
Yeah, hopefully.
Okay.
Okay, thanks a lot.
Thank you very much. All right. Take care, everyone. Have a nice weekend. Have a good evening. Okay. Bye-bye.
Bye.
Bye-bye.